In this video, I'd like to discuss some of the vocabulary that I've been using in some of the other videos, specifically the feature engineering video that came out this week. I want to just go over some of the vocabulary that was in there. It's covered in reading, so you'd find it in the readings. Of course, I'm sure you're doing those readings, but I want to make sure we have some coverage here in video form as well. One of the pieces of vocabulary that I had in that feature engineering video was labeling, and I also used the term leakage. Let's talk about both of those. So if we think about a flashcard analogy for labeling, the teacher shows you a flashcard and shows the wrong word on the back of the card, then you learn the wrong thing, right? If you had a flashcard for learning vocabulary. Well, that's what happens when labels are sloppy, the labels that we work with data. Labels are basically the answers that you want the model to learn. And so when we have that label that's faulty, then it's not going to be great. Labeling is simply the process of giving each row in your data set the right answer. So if you're training an email spam filter, every email in your data set needs a label, spam or not spam. It's that simple. If you're training an intrusion detector, each row of traffic is labeled normal or attack. Think of it like an answer key on a worksheet. Without those answers, the system has nothing to learn from. Leakage, on the other hand, is what happens when we accidentally let the answers sneak into the features. So imagine you're training a model to predict whether a student will pass a course, and one of the features is final grade. Well, that's sort of cheating to get there, right? The model then already has the answer hidden within its inputs. In cybersecurity, leakage might look like training on a data set where the timestamp of when the log was flagged is included as a feature. That tells the model more than it should know and makes the model look smarter than it really is. So labels are the answers that you want the model to learn. Leakage are the answers hiding where they don't belong. Let's look then at class imbalance. Class imbalance is something that we run into, and it's simpler than it sounds. Imagine you have a data set of 1,000 network flows. 999 of them are normal, and only 990 of them are normal. Only 10 of them are attacks. That's imbalance. The normal class within there, the things that we would label normal, are much more common than the things that we've labeled attack within that data set. So why is that a problem? Well, because a lazy model can then just guess normal every time, and it will be right 99% of the time. Think about that, 990 out of 1,000. And if we build a model, the model just guesses, normal for the traffic because 990 of them were labeled normal. And so then we would be able to say our model is 99% accurate. Well, in fact, it's that we fed bad data in. And so then we fed an imbalanced class of data into that model to learn from. And so it's just going to guess normal every time, and it'll be right 99% of the time. Cybersecurity data almost always has that imbalance. Attacks are rare compared to the ocean of normal traffic, and that's why we need to pay attention to class imbalance. Even though at first it sounds like just a little bit of a math detail or an extra detail, it's something we definitely need to pay attention to, not only for cybersecurity, but when we're building an AI model in general. So what do we do about imbalance? Well, we can balance that data set. So that means making sure the model sees enough examples of each class. Sometimes we collect more attack data. Other times we duplicate those rare cases to just simply give them more weight. Second, we can change how we measure success. Instead of only using accuracy, remember 99% accurate, because we fed bad data in. So instead of only using accuracy as a measure, that'll just sort of hide the problem. We can use metrics that focus on how well the model finds those rare cases. Third, we can design our training to care more about catching that rare class, the attacks, even if it means a few more false positives or false alarms. In cybersecurity, missing an attack is usually far worse than investigating a few extra false positives. Here's another simple but important idea. It's feature scaling. Suppose one feature in your data set is packet size, which ranges from 1 to 1,500. Another feature is protocol type, which is just 1, 2, or 3. If we don't adjust, some models will treat packet size as way more important just because the number is bigger. It is truly that simple, and it does truly happen, the scaling of that feature, because the packet size, even though they're not related at all, and we know they're not related, the model doesn't know that they're not related. Scaling means adjusting those numbers so that they're roughly on the same scale. Think of it like normalizing different units. Comparing inches to miles directly is silly unless you first convert them into the same frame, so into the same unit of measure. When features are scaled properly, models can actually see patterns instead of being distracted simply by those big numbers. Sometimes our features aren't numbers at all. Maybe we have a feature for a protocol with values, string values like TCP, UDP, or ICMP. That'd be pretty common. Computers don't understand words like these directly. They only understand numbers. So we need to encode those categories into numbers. The simplest way is just to assign codes. TCP would be 1, UDP would be 2, and ICMP would be 3. That step is called encoding. It's nothing more than translation, turning categories into numbers so the model can use them. We're going to talk more about encoding as we continue to move forward, but the idea here is that we encode things into numbers. But now remember, I'll go back a slide, remember feature scaling, because now we have numbers and we've converted things to numbers. We want to make sure that we're converting and only using numbers that matter. We've just simply chose 1, 2, or 3 for TCP, UDP, and ICMP, but packet scale, packet sizing matters. And so that could matter in a cybersecurity context. We want to make sure that we are seeing the patterns or helping the model to see real patterns within there by scaling those features and making sure we're using the same units of measure. When we talk about feature selection, we're asking out of all the possible columns in our data set, which ones are actually useful. This is an incredibly important step in building an AI model, not just for cybersecurity, but an AI model generally speaking. So imagine you're trying to predict whether an email is spam. Some features matter a lot, like does it contain a suspicious link? Others might not matter at all, like length of the email subject line. So how many bytes are in the subject line of the email? Including too many irrelevant features can confuse the model. It can slow it down and sometimes even make it less accurate. Filters are one family of methods for feature selection. They don't look at the model itself. Instead, they use simple math checks to score each feature. For example, they might measure how strongly a feature correlates with the label. High-scoring features are kept, low-scoring ones get dropped. Think of the filters like a quick screening test. Before you train a model, you can filter out the features that obviously aren't worthwhile to keep within that model. Again, thinking of subject line in a spam email, probably not going to differentiate between a normal email and a spam email just based on the subject line. Probably won't differentiate between normal or spam and not spam for that email. Another way to do feature selection is with wrappers. Instead of scoring features with math tests, wrappers actually use the model itself to decide. Process works like this. We train the model with one set of features, we see how well it performs, add or remove some features, and try again. It's a manual process. Keep the set that gives the best performance. This is slower than filters because you're training many models, but it can be more accurate. Wrappers are like testing different ingredient combinations in a recipe. You don't know until you actually bake the cake and taste it if that combination of ingredients worked well. Now let's talk about dimensionality reduction. It's a big phrase, but it boils down to this. When you have too many features, you try to compress them into fewer, more meaningful ones. Dimensionality just means the number of features. If you have 100 features, well, that's 100 dimensions. So why reduce? Well, we just talked about that. Because highly dimensional data is hard to work with. Models get confused. Training slows down. Patterns just get buried inside of all of that clutter. Dimensionality reduction tries to keep the important signal while dropping the unnecessary noise. You can think of it like compressing a photo. You keep the important shapes and colors while throwing away tiny details that don't matter for the big picture. And when we think about dimensionality reduction, that's exactly what we're doing. We're throwing away things that don't matter to telling that story or to helping us build or train that model. Here's an example that we look at that has, let's say we have many different features. We're trying to train a model to determine if an email is spam or not spam. And we end up, after dimensionality reduction, with two different groups, two different clusters that absolutely help us work through it. So if we have 100 features that maybe describe word frequencies in emails, how often does the word prize or money or urgent appear within the email? Well, that's a lot to manage. We might have 100 separate features about that email, 100 separate details about each one of those emails, and where the goal is to reduce that reduce the number of features that we have. Dimensionality reduction is the goal. We want just the features that help tell the story. So we want to compress them into just a few new super features that summarize the key patterns within those emails. The result is a smaller, easier to handle dataset that still captures the important differences between spam and normal emails, and also makes things like visualization possible. With 2 or 3 dimensions, you can actually plot the data and see those clusters or separation. So on the left-hand side, we see the dataset with just 2 raw word frequency features of 100. It looks very noisy and overlapping. On the right, we see the same data after dimensionality reduction with principal component analysis, or PCA. We'll talk about that in a second. The classes are separated more clearly into 2 dimensions that capture the key patterns. So that visualization gives you before and after dimensionality reduction and should hopefully help. Let's talk then about principal component analysis. PCA, principal component analysis, is something that, again, you have the 100 features in that email, and the idea is with PCA to compress those 100 features into super features that summarize the important patterns. The super features that we have are called principal components. That's why we call it principal component analysis. Each one is a combination of the original features. It's chosen so that it captures as much variation in the data as possible. Again, let's go back to that photo example. Real world that we live in is 3D, but when you take a photo, it flattens it to 2 dimensions while keeping the most important information. PCA works the same way. It reduces dimensions while keeping the structures that matter. So in practice, PCA is just a tool for dimensionality reduction, turns many overlapping columns into fewer, clearer columns. So takeaways from this, went over some of the vocabulary that we've been using, and it does appear in the readings related to AI that have been provided, and hopefully you've found those readings and are able to get through those. Some of them can be rather long, I realize, but hopefully they're helpful, and hopefully this this video was helpful as well in giving you some additional context for the vocabulary that we've been using. The idea overall is to handle that imbalance. Remember, we talked about class imbalance as being problematic because if we have 99% of our traffic is labeled normal and only 10% or 1% is labeled as attack, well, then our accuracy isn't going to be very high with the model that we eventually train. And scaling and encoding are definitely important. We're called the packet analogy, the size of a packet being maybe 1,500 bytes. Well, now if we have something else that's encoded as a 1, 2, or a 3, the model might try to not scale those things and think that the 1,500 is much more important than the 1, the 2, or the 3. So we have to make sure that we're scaling things accordingly. And then the idea is to reduce the features that we have, reduce the columns to the important ones. What's important about an attack? What makes traffic look like an attack versus normal traffic would be a great example there. Idea is to simplify while keeping the signal and reducing the amount of noise that we have within that original data set. So I hope you found this video helpful. Thank you for watching.